In this video, we're going to see how do we do hypothesis testings for proportions in Excel. First example, a coin is tossed 1,000 times and 570 heads appear. At alpha equals 0.05, test the claim that this is not a biased coin. Does this suggest the coin is fair? Alright, so let's see what we have. Our n is our sample size, that's 1,000. And we're looking at the number of heads for our success, so that's 570. So our p hat is x over n, so that's 570 divided by 1,000. Q hat is the complement of p hat, so 1 minus p hat gives us q hat. So our p hat is 0.57 and our q hat is 0.43. Since this is a hypothesis test for proportions, we need to do the check to verify that we can approximate this distribution by the normal distribution, that nothing weird is going on. So we need to check n times p and n times q. So let's see, we need to figure out what we're saying for p and q. Well, it's saying test the claim that this is not a biased coin. Well, if something's not biased, that means that it's fair. So if it's a fair coin, that means that heads appears half the time. So because we're claiming that this is not a biased coin, that means it is fair. So that means the proportion of heads is equal to 50%, and the proportion of tails is also equal to 50%. That's what it means for a coin to be fair. So that gives us an assumed value for p of 0.5. So when we test n times p, that's going to be 1,000 times 0.5, which is 500, that's fine. And then q is also 0.5, so n times q is going to be 1,000 times 500 also. Oh, what did I do? 1,000 times 0.5, not times 500. Alright, so n times p and n times q are both greater than or equal to 5, so we're good. So going back to our hypotheses, we're claiming that it is not a biased coin, which means that it's fair. So our H naught is that p equals 0.5. So the complement is that p does not equal 0.5. And I know this is kind of rudimentary symbols here. We could go up to the symbols menu and find a not equal to sign, but I think this is good enough for the purpose of figuring out how to do these tests. Alright, so I think we have everything that we need. So because this is an equal to not equal to case, it's going to be a two-tailed test, which means alpha is going to be split up evenly among the two tails. So since alpha is 0.05, if we split that in half, that means 0.025 is in each one of those tails. So to find our critical values that separate the tails from the rest of the graph, we need to use our norm.s.inverse function, and I'm going to put in the area to the left of that bottom tail, which is half of alpha, so 0.025. And the plus or minus of this value gives us our two different ZCs. So the cutoff on the negative is negative 1.9600, and the cutoff on the positive side is positive 1.9600. It's nice that we can do it once, and since it's a symmetric curve about 0, we can just do plus or minus to get both of them. All right, so we have our two-tailed test, we have our critical values plus or minus 1.9600. Now we need to come up with our standardized test statistic. So plugging into our formula, we have p hat minus the assumed value of p, which is 0.5, divided by the square root of p, 0.5, times q, which is also 0.5, divided by n, which is 1,000. So we get our z to be 4.4272. That's a huge number. That is definitely above our positive critical value of 1.9600. Rounded to 4 decimal places, it's 1.9600. So it's definitely way up there in the rejection region. So since our standardized test statistic falls way up high in that top rejection region, our verdict is to reject H naught. So we can say that at alpha equals 0.05, there is enough evidence to reject the claim that this is not a biased coin. So to actually answer the question, no, the coin is not fair. It is weighted towards the heads. It is definitely not showing tails the right number of times for it to be a fair coin. So again, we had our values that we read from the problem. Yes, we didn't really need Q hat. We never used it, but we calculated it. The tricky part, I think, on this one was interpreting from the words to the math, because it's claiming that the coin is not biased. That means the coin is fair. So that means heads and tails show up 50-50. We did our check, And then we said, all right, since it's an equal to, not equal to case, it's a two-tailed test. So we split alpha up, half of alpha goes into each tail. We did norm S inverse of the area to the left of that bottom tail to get our critical values. And then we plugged in to get our standardized test statistic, saw that that fell way up high in the rejection region, so we rejected H naught, and there was enough evidence to reject the claim. All right, one more. So it says, an airline claims that the no-show rate for passengers is less than 5%. In a sample of 420 randomly selected reservations, 19 were no-shows. At alpha equals 0.01, test the airline's claim. All right, so our sample size, 420. Our success is actually a no-show, so it's not really a positive success, but that's what we're considering to be a success. So our p hat is the 19 over 420. So our claim, our H naught and our H sub A, let's see, they're saying that the no-show rate is less than 5%. So that tells us our proportion is less than 0.05. And that's our claim. It's going to go in H sub A because it doesn't have an equal to sign. So the complement is that P is greater than or equal to 0.05. Okay. So to do our check, we need to look at N times P and N times Q. All right, so our N is 420. Our assumed value for P is 0.05. That gives us a number that's bigger than 5. Not a whole lot, but it's bigger. And then let's see, P is 0.05, so that means Q is 1 minus P. That's going to be 0.95. So 420 times 0.95 gives us 399. Those are both greater than 5, so we can do the problem. All right, so because H sub A is pointing to the left, this is going to be a left-tailed test. So when we draw our bell curve, all of alpha goes in the left tail. So when we go to find our critical value, we go to norm.s.inverse, and all of alpha is in the left tail, so we'll put that into our norm S inverse function. And then we need to get our standardized test statistics. We look at p hat minus the assumed value for P divided by the square root of P, which was 0.05, times Q, which was 0.95, divided by N, which was 420. And we see that that negative 0.4 is not all the way past negative 2.3. So it is not so far to the left that it's in the rejection region. So our decision, let's go down too far, our decision is fail to reject H naught. Since our claim is in H sub A, all we can say is that at alpha equal to 0.01, there is not enough evidence to support the claim that the no-show rate for passengers is less than 5%.